and get us familiar with your work. And it's your time, Alessandro. Thank you again.
Yeah, thank you for organizing these seminars, and thank you for inviting me to talk. Are you seeing the presentation? Okay, great. I'm Alessandro Ruzza, a PhD student from the University of Milan, and I work on simulation-based inference for characterizing protoplanetary disks and young planets that might be embedded in them. So today I would like to talk about my latest work, which is the development of this tool, which we call the DBNets 2.0, for characterizing young planets in protoplanetary disks from dust substructures. So the paper is ready. It's going to be submitted soon, but it's not. This work is not published. So I would like to start first of all by answering this question. So what is the meaning of the term simulation-based inference, which is what I work on. So often in physics or in science in general, we have models. We develop models that depend on some parameters. And then we have data that we observe, and we want to try to fit these models to the data to infer these properties, these parameters of the model. So basically what we want to do is infer the posterior for the model parameters given the observed data. And this is often easy to do if you know how to write down the likelihood for your data, but that's not always possible. Indeed, in a lot of cases, it's not. It's instead possible, I mean, in many of these cases, when it's not possible to write down the likelihood, it's possible to sample from it using a simulator. So something that simulates the physical process that you are trying to study. And simulation-based inference is a term that describes all those techniques that use samples from the likelihood obtained in this way, so using a simulator, to then learn the posterior distribution for the model parameters given the observed data. So DBNets is a tool that I developed and published last year that does that on dust continuum observation of protoplanetary disks. So assuming that we all know that substructures are ubiquitous in dust observations of protoplanetary disks, and one way in which we can explain these substructures is by assuming that there are planets in there, generating them through planet disk interaction. Under this assumption, DBNets takes as input an observation showing some gaps or rings, and provides an estimate for the mass of the planet that may have generated that substructure. And the reason why we developed this tool were well, first of all, because we need to measure young planet properties. That's because the traditional techniques in which that we can use to detect exoplanets do not work very well around young stars. And it's clear if you look at the distribution of exoplanets that have been detected so far with respect to the age of the star around which they have been detected. You can see that less than about 10 planets have been detected around stars that are younger than 1 million years, so approximately what we think could be the timescale of planet formation. But we need to measure the properties of these young planets to really understand how they form and evolve in the early stages. And the ways in which now people infer the mass of planets, of possible planets that may have generated the substructures that we observe in the dust, have some problems. There are some empirical formula that, however, are not very accurate. They cannot take into account the full morphology of the substructures that we observe. Or another way in which people try to run this inference is by running fine-tuned hydrodynamical simulations. But this approach is very expensive is a computationally expensive approach. So we wanted to provide a way that was faster and more accurate than the traditional methods that now people use to do that. And then another problem of these traditional methods was the way in which uncertainties are quantified. So we really focused on developing a method that could quantify the uncertainties accurately. So the question now is, why did we develop a new tool? And to answer that, I would like to show you some empirical formulae that have been proposed over the years to link some features of the gaps that we observe in dust observations with the properties of the planet that may have caused them. For example, here the planet mass. You can clearly see that there is a link between the gap width or depth and the planet mass, and thus we can estimate it from the gap morphology. But in this formula, there are also some other dependencies from other disk properties. So it's clear that there are degeneracies, which means that we can have the same substructure in the dust with planets of different masses if other properties of the disk were different. And we want to look at these degeneracies to understand them and try to unveil them in order to have a better estimate of the property in which we're interested, which is the planet mass. But this also means that there is some information in the substructures about these other disk properties, so it might be able to get an estimate of them. So basically, the new objective for this new tool is the full joint posterior for not only the planet mass, but also other disk properties, which are the disk viscosity, the aspect ratio, which is just the disk scale height, and the dust Stokes number. So in the next slides, I would like, first of all, to explain to you what is the pipeline that we used in this new tool. Then I want to convince you that it works. So I'm going to show you some results that I obtained applying it on synthetic observations, for which we know the actual values of these properties, so we can test it. And finally, I will show you the results that we obtain applying the full pipeline to actual observations. So let's start with how the pipeline works. The previous tool, DBNets, so the previous version of this work, we were just using an ensemble of convolutional neural networks that were taking as input the observation of the dust continuum emission of a disk, showing some substructures, and were providing an estimate for the mass of the planet that may have caused those observed substructures. Now the new pipeline is instead divided in two steps. We are still using convolutional neural networks, but this time we're using them to summarize the input data into a set of summary statistics, so to compress the input data into in a lower dimensional feature space. Then we're using these summary statistics as input to normalizing flows to then get an estimate for the posterior that we're targeting. The reason for this pipeline is that we wanted to use normalizing flows because they are a very powerful density estimator with which we can, in theory, approximate every functional form for the posterior distribution. But they are quite difficult to train with high-dimensional input data. So for this reason, we used a convolutional neural network to summarize the input data into a lower dimensional feature space. And in this way, we can also exploit the inductive bias of convolutional neural network, which means that they are designed specifically for working with inputs which are structured, like, for example, images, and exploit their specific features. Okay, then we trained this pipeline on synthetic observations. And I want to stress here that what we get at the end is this posterior, and you should interpret it as a posterior conditioned on the model that we used to train the synthetic observations that we use to run to obtain the synthetic observations that we used to train this pipeline. So what is this model? This is the pipeline that we used to generate these synthetic observations. We run two-dimensional hydrodynamical simulations with only one planet fixed on a fixed non-eccentric orbit. Then we compute the brightness temperature of these disks with the simple analytical equation. And finally, we convolve the brightness temperature with Gaussian beams to simulate the finite resolution of actual observations. So, and then we use, of course, these synthetic observations to train the pipeline that I've shown you before. So, does this work? These are the results that we obtain on, again, on synthetic observations. Not the same that we use for training, of course, other synthetic observations. So here I'm showing for each parameter that we are inferring, plots that are showing our estimates versus the target values. And so the shaded areas here are indicating the regions between the 16th and 84th percentile of the distributions that we are inferring. And you can see, I think, two things from these plots. The first one is that the medians of the distributions that we infer are very close to the target values. So and the target values are always within the uncertainties. So our estimates are accurate. And also, I want to mark on the fact that our tool has a better precision on the planet in estimating the planet mass with respect to the other properties. And this is interesting because it's telling us that there is more information on the planet mass in these substructures than the other properties. But again, also we are still able to infer the other properties. So there is still something that could be learned from the substructures about the other disk properties. Now, these plots are giving you an idea of how accurate are our estimates, but they're not actually testing the accuracy of the full posterior that we're inferring with our tool. And to test it, we had to use a specific test, which is called TARC test, which was developed by Lemos and others in 2023. I'm going to explain to you briefly how it works. So let's assume that we have a density distribution function that we are trying to, that is our target. It's this P here. And let's assume that we want to approximate it with some density estimator, which is the Q here. That depends on some parameters that we are optimizing to make this a good approximation of our density function P. Now we can take from this density function some what we call credibility regions, which are regions of the parameter space for which the integral is of this distribution is equal to a certain value alpha that we call credibility level of the credibility region. Then if we take samples from the target distribution and we compute how many times these samples are within these credibility regions, and we call this how many times we call this expected coverage probability, we expect if our approximation of the actual density is a good approximation of our target, then we expect the expected coverage probabilities that we compute to be equal to the credibility levels of these credibility regions. And we have to do that for all levels of credibility to test these. If these distributions are the same, then this implication is always true. However, we're interested in the opposite direction of the implication, and the TARC test is exactly based on a theorem that states that the opposite implication is also true if this equality, ECP equal alpha, is true for all the credibility region that you construct for every alpha around every point in the parameter space. So basically what we want to do is compute this expected coverage probability for every level of credibility and see if our curve lies or not on the diagonal here. And these are the results that we obtain. In blue is the result that we obtain using the full pipeline that we developed. And in red instead is the result that we obtain using only the first step of the pipeline, so the convolutional neural network. So this is to show you that our pipeline is indeed accurate. The posterior that we get at the end is an accurate estimate when tested on synthetic observations. And we cannot use only the first part of the pipeline, but we really need to use both parts to get an accurate estimate. Okay, so finally, let's move to the application of this pipeline to actual data. I think that this tool can be used mainly in two scenarios. The first one is to run what I would call population studies. So you can start from the assumption that all the substructures that we observe are due to planets. Of course, this is not true. We don't know if it's true or not, but let's start from this assumption. And then from this assumption, you can derive what would be the implications in terms of regarding the properties of the planets and the disks. And this is what we did. So we gathered this data set of 44 disks for a total of 49 gaps and or cavities within them, and we applied the tool to each one of these substructures, assuming a planet in each one of them. And these are the results that we obtain, all summarized, all put together. So the corner plot is just to show you that we didn't see any particular correlation between the different properties in general, gathering all the results together. But the thing that we found interesting here are the values that we infer for the viscosity and the aspect ratio. So we found that these values are would be typically low, which means that also their product should be low. And we interpreted this as meaning that the so basically you can write this product as the ratio between the dynamical time scale and the viscous time scale of the disk evolution. And our results are implying that viscous time scales of these disks should be very long. And you can try also to measure this ratio of time scales, assuming the self-similar solution for the disk evolution, and as you can write this ratio in terms of the mass accretion rate onto the star divided by the disk mass times the omega, the angular velocity of the disk. So if you measure these properties here, so if you try to get the values for this product, measuring the star accretion rate and the disk mass, you get typically higher values than what we get instead from estimates for the disk viscosity and the disk aspect ratio from local estimates looking at the effects of what we assume to be planet disk interaction. So a possible interpretation for that could be that to reproduce the star accretion rates that we observe, you would need some additional mechanism for angular momentum transport in addition to local mechanisms such as viscosity. And finally, we look at the distribution for, we look at also at the planet masses that we infer. I'm showing here the plot, a plot for the planet masses that we infer for these disks versus the semi-major orbital axis where we assume the planets to be. Okay, well, you can see that the planets that we propose from the substructures lie in a region that it's not covered by traditional ways in which we detect exoplanets. And then the interesting thing here is that we typically observe low values for planet masses, typically lower than 1 Jupiter mass, which is consistent with the fact that we are not detecting these planets through direct imaging surveys. So finally, the other use case that I can think of for this tool is its application to single disks. So for example, let's assume that you have a candidate planet from some direct imaging observation. You can use this tool to check quickly without running hydrodynamical simulations if your candidate planet is or not consistent with the dust substructures that are observed. And the ideal case to test this tool is PD70, because of course we already know that there are 2 planets in there. It's not exactly any ideal case because my model is with only 1 planet, but here I'm applying it to the assuming the planet in the position of PD70C, which is the closest to the ring. So we can assume that the morphology of the ring is mainly determined by this planet. And here is the result that I'm obtaining. The interesting thing here is the planet mass that we are inferring, which is approximately around 5 Jupiter masses. I don't know whether or not the title, sorry. It's about around 5 Jupiter masses, which is consistent with the estimates that for example, that come from stability studies. Okay, so here are my conclusions. So to conclude, I've shown you DBNet 2.0, which is a new tool that can provide an accurate estimate for planet mass, but also other disk properties. Compared to other methods, it's faster and more accurate than the more traditional methods. And looking at its application on actual disks, the main results that we found were that we get typically low values for basically all of the properties that we infer. So for viscosities, aspect ratios, and of course the more interesting are the planet masses, which are typically lower than 1 Jupiter mass. Okay, thank you.
Thank you, Alessandro, for your wonderful talk, and it was very interesting. So if there are any questions, please, I didn't see any in the chat room, but if someone wants to ask, you can raise your hand and ask. Any questions for Alessandro? Yeah, Edward?
Yeah, thank you. This plot is very interesting. On the right bottom, right, the planets, the masses there, the positions. I saw similar plots done by other groups like Laudato. Do they agree, these estimates, your tool, with other estimates of other groups who also try to derive planetary masses based on the geometry of the gaps? And
okay, well, I directly tested only against the Laudato masses.
So it's okay. That's are there any other estimates than Laudato?
Yeah, I think there are. I mean,
well, yeah, but with Laudato, it's an independent estimate, right? Okay, yes. I see. So there is some agreement, but not complete, right?
No, there is still some scatter between the estimates. I mean, which is expected because the Laudato estimate is just done relating the gap width with the planet Hilda radius. So it's a very simple estimate. And the reason why I only tested it with these, it's that I mean, it's the only sample, it's the only method for which I can that I can apply quickly to the entire sample that I analyzed, so I can get a comparison.
Oh, you also mentioned that most of the planets are below Jupiter in mass, right?
Yes.
That's why it's difficult to directly image them. But there's still a few of them are above the Jupiter mass, right? So they even 5 or something Jupiter mass, right? They should be directly detected. So why we don't see them? Any explanation?
Okay, I haven't looked at the observational limits for this system specifically. I think that still when the mass is above, I mean, is of a few Jupiter masses, it might be that we're not detecting it because they are too cold. I mean, or because there is some extinction from the disk.
Yeah, because direct detections of several Jupiter masses, it's not uncommon.
I mean, it may still be that.
But at much later phase, of evolution, 100 million years. Okay, thanks.
Thanks.
Any other questions? If there aren't, I would take, I have one question, and it's about the corner plot and the variables that you have used the correlation between. You said that we cannot use a lot of variable, but what's the maximum number of the variables correlations that we can use here in your practice? Are those 4 only, or we can make a correlation between different other variables like the eccentricity or something like that?
No, I haven't looked at the eccentricity. Sorry, I don't think I'm getting your question. Are you talking about this corner plot here?
Yeah, the corner plot, but it gives only the 4 variables. Can we use? Yeah, can we use more variables? And what's the maximum number that you can use with your simulation?
I mean, I'm only inferring these 4 variables, so that's why I'm only showing this 4. There might be correlations between combinations of these variables instead of just.
But can it be done with the simulation?
What?
The others? The other variables, like as I mentioned, the eccentricity or any other.
I mean, you could run simulations barring other variables. I mean, the reason why we didn't do that, we didn't include them, because we would have needed a huge number of simulations. Of course, if you increase your parameter space, the number of variables, so the dimension of your parameter space, you would also.
Yeah, that was pretty much how many parameters you can use.
I mean, in principle, you can use how many you want. We started from like a simple model because you still run. I mean, in this work here, we used 1,000 simulations to cover a 4-dimensional parameter space.
Okay, thank you.
Okay.
Thank you. Do you have any other questions? Okay, thank you, Alessandro, once again for your wonderful talk. And I will give the place now to Edward.
Thank you.